Hello, everyone, and thank you for attending today's webinar, PLAXIS Introduces Norsand Model with creator Mike Jeffries. Before we begin, we do have a few housekeeping items we'd like to cover. At the bottom of your screen are multiple application widgets you can use. All these widgets are resizable and movable, so feel free to move them around to get the most out of your desktop space. You can expand your slide area or maximize it to full screen by clicking on the arrows in the top right corner of the widget. If you have any questions during today's session, please submit them through the Q&A window. We will try to answer as many questions as we can during today's session, but we can follow up later with you via email. Please know we do capture all questions coming in. Additional help materials are available in the resource list, so we encourage you to download any resources or bookmark any links that you may find useful. For the best viewing experience, we do recommend using a wired internet connection and closing any programs or browser sessions running in the background that could cause issues. These webinars are bandwidth intensive, so closing any unnecessary browser tabs will help conserve your bandwidth. The webcast is being streamed through your computer, so there is no dial-in number. For the best audio quality, please make sure your computer speakers or headset are turned on and the volume is up so you can hear our presenter today. If your slides are behind or you're having any audio issues, try pushing F5 on your keyboard to refresh your page. There's also a help widget at the bottom of your screen to help with some other common technical issues. And lastly, an on-demand version of this webcast will be available approximately 1 day after today's session and can be accessed using the same link that you used to join us today. So with that, I'll hand it over to our Bentley colleague, Sandro, to get us started.
Thank you. Hello, everyone, and welcome. My name is Sandro Brasile, and I will be today's moderator. I only have a very quick introduction on my side. As you all probably know, we have been working on and lately released an implementation of Norsand soil model with the PLAXIS product. I think you may have guessed as well that the author of this model was directly and personally involved in this journey, such that we could guarantee the delivery of the highest standard on this matter. I'd like to introduce today's presenter and speaker sitting virtually with me. Many of you, I guess, know Mike Jeffries from the book he wrote with Ken Bean, and which is based on some of the experiences you'll hear in today's talk. I have to say in just a few words, Mike is a product of a widely influential Imperial College school, where he was taught in particularly by 3 ranking lecturers, all of whom took, I would say, a rather rigorous approach to soil mechanics, and I expect this approach will be echoed today. Before we start, just a technical note. We are going to push 2 movie clips at the very beginning of the talk. Therefore, I suggest you to keep an eye on your media player window. And with this, Mike, I hand it over to you.
Hello, everybody. Good morning, good afternoon, good evening, as the case may be. I'm going to run through 4 topics today. I'm going to first off go at why you should be interested in Norsand. What is the offer of Norsand? What is its unique selling point? What can it do for you? You as an engineer, that is. I will then move on to where does Norsand come from. This is perhaps what you might be more expecting from the title of the talk, but I'll go through the history and why it came out of industry rather than our universities. Having done that, I will then go on to using Norsand. Remember, it's garbage in, garbage out. So you can use Norsand by firing up PLAXIS and saying, yeah, I want to use this block of soil as Norsand. But we need to think about the properties you assign and the soil state you assign. So I want to get into a little bit about how you use it and how you use it properly. And for many of you, I'm going to be using language that's not going to be that familiar. I'm going to run you through 100 years of soil mechanics history in an hour flat. And every time I've given this talk, or versions of this talk, people walk away with their heads spinning. So in the end, I'm going to touch on some educational resources. If I've done a good job in my hour, you'll be enthused, and I've got some places where you can then go to pick up extra information. Okay, let's look at the why you should care about Norsand. And this is really back to ourselves as an industry. I'm sure pretty well most of you, if not all of you watching this video or this webinar, have seen this video. It's the dam failure 2 years ago. And there are a number of interesting aspects to this, but the two gentlemen you see on the inset are two of the Valley executives. And they make the point in the video, and you can find the video on YouTube. They are feeling betrayed. They're saying, we put in all the piezometers that our consultants asked us to install. We put on a computer aided monitoring system, and we put in settlement sensors, and the whole lot. And there was nothing, we've done everything I've asked of us, and this dam has failed. So in the end, the story of this dam failure is actually a failure of you and me as engineers. We have a lack of understanding of soil behavior within our profession. And really that is the ultimate what Norsand has to offer you is, in fact, it's critical state theory in general, is that it tells you why some of the things that happen, why they happen. Now, to cut to the chase, I'm going to show you two videos. I'm going to run a little bit of this video here, which is the video you've seen before, or most of you have seen before. You'll see the failure initiate top right of the dam. And what I'd like you all to do is when you see it initiate, just start counting down the seconds as you watch the failure propagate. Because what the message I'm trying, or what I'm trying to get you guys to pick up from watching the video is the speed of propagation. Now remember, when we start rolling this video, the piezometers are showing no excess pore pressure at all. These executives did not lie. So let's now try and push the video and see if we can see what happens. Here we go. Now, I don't know what you counted, but I reckon it takes about 5 seconds from drain conditions to a full undrained flow slide. Now, cutting to the chase, I want to take you now to another liquefaction case history. What you're looking at here is a tailings dam in northern Alberta. It's up in the Fort McMurray region, which is where the oil sands are located. The photograph you see on the left is the dam. At this stage, she's 100 meters high, as I've indicated on the slide. You can see the tailings pond indicated on the photograph. At this point, the dam is topped out. It's now closed and reclaimed, but this is just before they did that. The bottom cartoon, I flipped it inside out, so it matches visually the photograph. And what you can see there is the Sawtooth thing, where you're looking at a dam that's been constructed by the upstream method. And what happened is these guys were back in 1970s when they first started building this dam, they had a number of liquefaction slumps of these upstream construction as they were pushing out on the tailings. And the nice thing about these slumps is that you can treat them almost as test loadings because it's a very simple geometry and it's a very simple crest load being applied. There's no funny foundation behavior. There's no funny water pressures. It's a very simple loading geometry. And so it makes a lovely test case for us to say, okay, can we understand this drain to undrained transition? So what you're now looking at is the Plexus model we've used to look at this, these flow slides and how they initiate. The photograph shows one of these raises being pushed out into the tailings. And you can see they're really quite steep slopes these guys were producing. The cartoon or the picture below is the the Plexus model. You can see the elements in there. The dark blue block with the sawtooth, as it were, that is our dam being raised. And you'll see when we run the animation, you'll see the fill being placed and the raise going up. The raise went up 12.5 meters, and they did it in a period of 3 months. And you'll see a transition into a full flow slide. Everything is drained until the last minute. The color coding on the right-hand side is the mobilized stress ratio, eta over m. I'll define what those variables are later in the talk, but the only thing you need to know at this stage is when we go red, we're into the critical state, and we've got a full liquefaction. So when we're in these sort of pale green and blue colors, we're in a nice drain condition, we're building the dam, and then we watch it flip into an undrained flow slide. So let's see if we can push the video to you now. Video's coming. And you can see it going, and there she goes. And notice the settlement. You see the settlement coming down. We're using Plexus in the large deformation mode. So we're automatically picking up the residual as well as the peak condition. And this is exactly like Brumadinho. We have loaded all the way up, drained, and then we pose a question, can it take an undrained load? And the answer is no, she falls down. Now at this stage, what you're looking at is a bit of a technology demonstrator. That doesn't answer the engineering question, why you should care. Well, the why you should care is this. As an industry, we've had 6 large dam failures in 30 years. You can see on these photographs another 4 of them, and these are company-threatening events. The damages go into billions. And the question is being raised now in financial circles, can mining companies be invested in? This is really far outside societal tolerance. And the mining industry has responded with the International Council for Mining and Metals, which is this clip of their website you see on the slide here. And they've promulgated this global industry standard on tailings management. And they're saying, they posted a further press release earlier this year saying, well, we haven't achieved very much in 2 years since the dam failure at Brumadinho. And that really is the context for why you should pay attention. What we have here with this implementation in Plaxis is a tool to address not only our customers' needs, it's the needs of society as a whole. We need to do a better job. This is a tool to help you do a better job. So what's the problems with tailings dams? And I should say here, because Sandra will point out that, yes, Norsand can do soil structure interaction and so forth. It can do all those good things. But really, right now, the most pressing problem for our geotechnical industry is understanding tailings dam failures. We have to get on top of this. And I should say, on one of the responses out of the initiative is they want better governance. So it's been very much directed into nominated engineers of record and things like that. And you're seeing things being floated about like people in these positions need 30 years of an experience and a PhD. Well, if that was sufficient, then those tailings dams failures I've shown you would not have occurred because people of that caliber were involved. We actually have a problem we've got a failure in geotechnical education on our hands. And the problem is simply this, that we are getting these dams and they're failing statically. There's not been an earthquake in sight. And they're failing from drain conditions in seconds. And so it's very common, every one of these, or most of them, had piezometers in there. And the piezometers are installed at the behest of their consulting engineers, such as you and I. And the piezometers are read and they say there's no excess pore pressure. And also there've been minimal deformations. And as a profession, we have enormous difficulty in understanding why this develops. And what is going on is what we have is under certain conditions of stress and certain conditions of void ratio, our soils are very sensitive to what I call an infinitesimal perturbation. That is, the proverbial butterfly wing flapping can make our dams fail. And the nearest analogy to this is if those of you with a civil engineering background, you remember your structural engineering component of your civil engineering degree, you'll have gone to a structural lab. We all do labs, and there'll have been a structural lab. One of your experiments would have been a buckling of a column. And liquefaction, or this static liquefaction, is analogous to column buckling. What is happening, we get to a particular situation of stress, and the soil is in a condition where there's a lower energy deformation mode, and it will just flip to that, literally with a butterfly wing. The one I showed you on Tar Island, the failure seems to have been triggered by literally a bulldozer moving across the surface. The vibration from that was sufficient to trigger the liquefaction. Now, the kicker is that the sensitivity to this perturbation depends on stress state and it depends on void ratio. And both of those are evolving as we build the dams and we stack the tailings behind them. And the problem we have is that limit equilibrium is our standard method for analyzing these dams, and it can't track evolving stresses. It cannot track evolving void ratios. So our basic tool, which we use in consulting engineering to look at dam stability, simply is not going to help us. So I have said that as a profession, my message to you today is we actually need finite element analysis using critical state theory to understand our dams. Now, some of you will say, well, we can do well enough with limit equilibrium, we make the appropriate choices of strengths and so forth. But what I say in reply is, well, if we have these dam failures, and whether it's Fundal, Brumadinho, or Cadia, if the boards of inquiry found that they had to turn on finite element analysis to understand how these failures developed, wouldn't it be better to use these finite element methods now rather than have yet another failure and a board of inquiry looking at you? So that's why I use the strong word, this is what we need as a profession. And this really is where this Norsand and Plexus fits in, because this is one of the tools that does this for you. It's a commercially available tool. This is not rocket science we're going to be dealing with. So what is this critical state theory, or what is its offer? Why is this so important to the story? Well, to tell you that now, I need really to go back into history to explain to you where this has all come from. If you think back to the 19th century, we had the Industrial Revolution. As part of the Industrial Revolution, we had quite a large movement of people from the farms and so forth off the land into cities. And the first thing you need when cities start getting built is you need water supply. And water supply, more often than not, involves building dams. And what you're looking at here is a dam. This is one of the dams for the water supply of Vancouver in Canada. This is Coquitlam Dam. And if you can look carefully on the drawing, you'll see this is dated 1912. And this dam was built by hydraulic filling. And the reason for that is you think of our fellow civil engineers of 100 years ago. We've got all sorts of earth-moving machinery today. If you want to build an earth-filled dam today, you've got 200-ton dump trucks. They had none of those things. But what they did have is pumps. So hydraulic filling was almost certainly in North America a standard method for building dams. And what it is, and it's like this, you put it in a rock-filled starter dike, which is what you see on the left, and then you slurry up your borrow in the borrow pit, and you pump it to the dam, and you just spigot it out. And you skim the water off or decant the water in the middle, and up she goes. Now, the problem with this, and the reason people did this, it was half the price of other methods of construction. And this is moving down the coast now from Vancouver to California. This is Calaveras Dam. And again, you can see on the photograph, you can see the spigot pipe and the fill being deposited. And if you look carefully, you'll see the site truck is actually a horse and buggy. I just love that. But the problem is this. This dam just as it was coming up to the final crest level, it went into a flow slide, just like Brumadinho. And if you consult the transactions of the American Society of Civil Engineers from this era, you'll find these sort of slides were commonplace. People kept using this method of construction because it was a lot cheaper, but they also accepted a chunk of these dams were going to fall down. Ralph Peck is famously quoted as saying hydraulic fill dams are reliable if they survive construction. Now, the big change came about, and the change came about with this dam. This is at Franklin Falls. It's in New Hampshire. It's about an hour's drive up the interstate from Boston on the east coast of the United States. And it was designed and constructed by the US Corps of Engineers. And the engineer of record was a chap called Colonel Lyman. And Lyman was determined that he was not going to have a liquefaction failure with his dam. In those days, it was called sand flow failure. They didn't call it liquefaction. Now, the insight Lyman took and which he used to base his engineering on, it was this bottom cartoon at the bottom of the slide. What you're looking at there is idealized packing of ball bearings or equal-sized spheres. And this idea was put forward by Reynolds, and the date on there is 1885, so late Victorian engineer. This is the same Reynolds of Reynolds number fame from hydraulics. Now, Reynolds' observation was, I can arrange spheres in various packings. And the packing on the left is the loosest possible theoretical packing of equal-sized spheres. That's the face-centered cubic array. The packing on the right is the densest possible packing of spheres. That's the body-centered cubic array. And what Reynolds deduced or observed was that if you distort either packing, the spheres have to move over each other. And that moving over each other will cause a change of volume. This is most easily seen on the right-hand scheme, which are the densely packed ones. It's easy enough to see if you distort that lattice, the spheres have to expand, or the array of spheres has to expand. Now, obviously, if you've got water in the void space and it's expanding, you're going to generate negative pore pressures, depending how fast water can get in. Conversely, on the left one, the spheres will collapse down and displace water, and you'll get positive pore pressure. That's how basically the flow slides develop. And what was interesting about Lyman, he set about having his fill systematically tested. And the testing was done by, or the professor involved was Arthur Casagrande. And the figure is, which is now come up on your screen, this characterization of soil behavior usually has his name on it, but when I read Lyman's report on the construction of this dam, I see Lyman very much as the guiding light in this idea. Anyway, what we have here is a shear box, which is the top left sketch, and they've done a series of shear box tests. And what they observe, and it's marked in as the plot A, is that if you have a dense sand and we shear it, as you all know, it dilates and we get a nice peak strength. And we had to shear a loose sand, we don't get a peak, it just goes to it just gently increases in strength as we displace it sideways. And what they found in their testing was that whether it was dense or loose, it went to the same ultimate strength. So far, so standard. But what they did was so insightful is they also tracked the void ratio. And you then have this plot B where the loose sand contracts down and the dense sand dilates, but they get to the same void ratio in the end. And the deduction that Lyman made was that that void ratio separated loose behaviors from dense behaviors. So if he achieved that in his construction, the dam would be safe, which is why it got called the critical void ratio, because that was their critical construction condition. Now, when they first put that idea out, they seemed to think the critical void ratio was something like an E-min or an E-max. It was a single number. But more or less concurrent with the Franklin Falls Dam, they were also building another dam up in Fort Peck, which is up in northeast Montana near the Canadian border. And that dam is another hydraulic fill dam, and that also had a flow slide, which is what you see on this photograph here. This is an aerial photograph from the day. And when you see this case history written up in the literature, you think the whole dam failed. Well, no, it wasn't the whole dam. It was just the a length of the dam out near the abutment. But they carried out similar critical state testing to what Lyman had instituted at Franklin Falls, confining stress. What today we would call a critical state locus, and that's the line I show in green there. And that line is actually taken from Don Taylor's book of 1948. Today, we know we can measure the critical state. It exists in sand, it exists in silt, and it exists in clay. The same idea continues. And we use a mixture of drained and undrained tests, and I'll get into the tests we use later in this talk. But the key thing is, as an industry, we now have a precision. We've done a cross-lab comparison, and we can determine the critical state locus with a tolerance of something like plus or minus 0.02 in void ratio units. You'll hear me talk about the soil property lambda, which is that pink symbol. That's the Greek letter L, and that is simply the slope of the green line. Generally, the semi-log line, this green line, is an okay fit, but it's not necessarily a perfect or the best fit for every soil. So it's become very popular these days to use a power law relationship for the CSL, and that's what I'm highlighting with that pink arrow. You can see the guys who did this testing have drawn a curved, or a semi-log thing. It looks curved. It's actually a power law. They've drawn that as an improved fit. In the Plexus implementation of Norsand, we give you a choice. You can choose the semi-log line or you can choose the curved one. And which one you choose depends on the soil you're working with. So you do the test and you choose what is appropriate. Okay, so much for the critical state locus. What is critical state theory? Critical state theory is an instance of the mathematical theory of plasticity, and it's the instance when we apply that mathematical theory to soils. If you do, when you think back to when you first learned soil mechanics and you've done some soil mechanics labs, maybe you did a shear box, maybe you did a triaxial test, and you usually just load them up. But you never really sort of question whether you learn the most from loading. The key observation that drove people was that if you do a triaxial test on clay, for example, and you bring it up to peak load, if you then take the load off, you don't get the deformations back. That is, the deformations are more or less permanent and irrevocable. And that is ubiquitous in soil. And that is plasticity. That's all plasticity is. You don't get your displacements back. And the theory of plasticity was developed from metals, but it gained enormous impetus in the Second World War as it got applied to the metal forming processes. But because soils were so ubiquitously plastic, there was much enthusiasm in the 1950s to take this mathematical theory and apply it to soils. And I also want to note here that there's certainly a current fashion to say that we can only understand soils on a micromechanical basis if we, by looking at the forces between the particles and looking at the network of how those forces are transmitted. To which I say no. The theory of plasticity is based on thermodynamics. And thermodynamics is probably the most fundamental thing in the universe after the relativity. It is that fundamental. And we gain our power in plasticity by casting things in a thermodynamic framework. Now, when we do this and we apply plasticity to soil, or for that matter, when we apply it to copper or aluminum, there are always three elements to plasticity theory. Element number one is a flow rule, and that just tells us the relative magnitude of the strain increments. How much strain is going north-south, how much strain is going east-west, how much strain increment is going vertically. That's the flow rule. The yield surface is a condition that tells us when do plastic strains develop. And the hardening law is really the controlling thing, because the hardening law tells you how the yield surface changes size or shape with plastic strain. And the key thing with critical state theory is we use the critical state locus as the basis of the hardening law for soils. And that's why it became called critical state soil mechanics, because we're using the CSL to control soil strength. Now, let me talk next about the flow rule. If you do a shear box test on dense sand, and as you push the shear box sideways, you'll see the top platen rise up. People in the night, bear in mind this sort of testing started in the 1930s, people very quickly said, well, if the top platen's rising up, it's doing work against the confining stress. And people of that era were very interested in trying to understand the origin and nature of soil strength. So they started saying, well, we must correct our strength tests for boundary effects, or this boundary energy correction. This went one stage further, because Don Taylor looked really back to Reynolds' cartoon, my little cartoon of ball bearings down on the bottom right of the slide. And he said, actually, this is really caused by the particles having to override each other. This is what is giving us extra strength effect. And he used the phrase interlocking for this, having this forcing of the ball bearings or the particles to ride over each other. He called that an interlocking component of strength. Friction was a true mineral-on-mineral sliding, where we actually have a frictional concept of strength. And Don Taylor said strength equals friction plus interlocking. Simple equation there in pink. You often find this idea in our soil mechanics textbooks as my cartoon there. It's the Sawtooth model of soil strength. And the idea is that soil doesn't shear horizontally, it shears on an inclined plane. And the friction on the inclined plane is the true friction, and the Sawtooth angle is your dilation angle. Curiously, Don Taylor never put an equation to this. The guy who put the equation to this was Alan Bishop. And the equation is the one I circled in pink. And he said the first left-hand side is a tau over sigma n, that's just short soil strength. And he said that was composed of tau f, our true friction. And then there's delta v over delta delta, which is our dilatancy. We still use this idea today, but of course now we cast it from a shear box, we generalize it into 3D stress and strain invariance. So we now say, rather than tau over sigma n, it's sigma q, which is the generalized deviatoric stress measure, sigma m, which is our mean effective stress, and the ratio of the two is this parameter eta, which is the Greek letter h, and that equals m, which is our friction. We now don't use an angle, we use it as a stress ratio, minus this DEV d epsilon q. And that's the incremental volumetric strain to the incremental distortion strain. And usually we refer to that parameter group as the letter D. So we have the simple equation, eta equals m minus d, and that's stress dilatancy. Now, the next step is this. This was the key thing for pulling the whole thing together. What you're looking at here is two graphs put on top of each other. So if you look at my y-axis, I said I'm plotting here sigma q, my deviatoric stress, but I'm also plotting, if you like, on a second graph underneath it, the distortional strain increment, epsilon q dot. The x-axis on the bottom is my mean effective stress, and also underlying it, my volumetric strain increment, epsilon v. And the words work conjugate is just a fancy phrase for that. If I multiply by sigma q by my delta epsilon q, and I multiply my sigma m by my delta epsilon v, I add them together, I've got the correct amount of work going into the element of soil. We need to do that because we are using thermodynamics. Now, the interesting thing that came out of thermodynamics that is, if I take a strain increment vector, which is what I'm showing with the pink arrow, there is a theorem. I don't mean a theory. I mean a mathematically proved theorem from thermodynamics that the yield surface will be perpendicular to that strain increment vector. So if you look at my pink arrow, you'll see underneath it, I have drawn at 90 degrees a blue straight line. So I have this theorem that says my yield surface is 90 degrees to my strain increment vector. So my yield surface is going to be related to that blue straight line. I know the direction of that pink arrow because that is the equation I've just shown you from the Taylor-Bishop model. That is d equals m minus eta. D being the direction of the vector. It's the ratio of the volumetric. Bear in mind, this is two graphs on top of each other. The horizontal component of that pink arrow is the increment of volumetric strain, and the vertical component is the increment of distortional strain. So that is dP. So I know what my vector is simply from my stress state eta and my soil property m. Now, high school algebra, everybody. When you do high school geometry, you all know that if you have a line with gradient x, a line perpendicular to that line has got gradient -1 over x. So we can apply high school geometry, and we can then say, okay, that light blue line has got a gradient of dq dp. And I know what that is because I can do it from my -1 over x, which is what I've done there. I've now got myself a differential equation. And you can integrate that differential equation. And when you do so, you get this bullet-shaped surface, which is what I've annotated as YS. That's the yield surface. Okay, and that's how it's been determined. We've taken a theorem, and we've taken the Taylor-Bishop strength idealization, and we've integrated. And that gives us our yield surface. Now, when you do an integration, of course, you always get an integration constant. And what these guys did, they said, okay, we like using the vertex of the yield surface, which is where the green dot is. We're going to take that as where we're going to define the integration constant. And you can see there I've drawn the green line, and that is given the slope of m, which is the critical friction ratio. And the reason for that is you'll observe the vector at the vertex is going straight up. My strain increment vector is going straight up. It's going straight up. I've got no volumetric strain increments, ergo, that's the critical state. They then made the great leap, and they said, aha, what about the critical state locus, what I've just been showing you a few moments ago? Well, if that is the critical state on my yield surface, I can go to my E log P plot, which is my cartoon on the right. That's also the critical state. Then those two things must be one and the same. So I have now got a relationship where I can go from a void ratio. The void ratio, I'm showing this point as the soil is maybe at a void ratio of 0.82 or whatever it is. That tells me the stress in the critical state, or the mean effective stress in the critical state, is about 40 kPa on this cartoon. That means my strength, or my axis on the horizontal axis there, my green dot is at 40 kPa. So I can now scale my soil strength behavior from its void ratio. And that is the elegance and power of critical state soil mechanics. This is the original Cam Clay model on one slide, and it's no more complicated than that. In essence, what we're combining is the top right information is what you get from an odometer, conceptually from an odometer test, and the strength information is a triaxial test. We're just combining two standard soil tests. And how well does it work? You'll find when you read about it, people always say Cam clay works fine for soft clay. Well, it does, that's true. But I like showing this data. What you're looking at here is a triaxial test, and a triaxial test on loose sand. And I like using loose sand just to make the point that the theory has no concept of geology. And the brown is what we've measured on our triaxial test on loose sand, and the blue is what Cam clay predicts. So stress strain on the top figure and volumetric strain, axial strain on the bottom figure. And I find this deeply impressive. You know, we've done a very simple exercise, essentially a back of an envelope thing with a few ideas. Boy, we're cooking with gas. We can actually get the details of soil behavior and the strength and the stiffness. Now, but it was not true in general. It's very easy to go to your lab and you can make samples quite a bit denser than the one I've just shown you. And what you do is when you're pluviating the sample to make it, you just gently tap the mold. And you can, I've done here, or the lab guy is here, they've made a sample, and the green line is the critical state locus. And they made a sample that's whatever, it's about 0.15 void ratio units denser than the green line, or the critical state. And the CAM clay prediction for the behavior of such a sample is what I show you here in brown. And what you measure is what I show you in blue. And as you can see, the CAM clay is out, and it's out not just by 10%. We're talking orders of magnitude here. It's orders of magnitude too stiff, and it's order of magnitude too strong. And this led to a great rejection of critical state soil mechanics. If you search critical state soil mechanics on Wikipedia, you'll find the words I put here on the slide in pink. They call it a degenerate research program. And that's their phraseology, not mine, where excuses are used to justify inability of the theory to match empirical data. And that is why most of you have not been taught critical state soil mechanics as part of your geotechnical education, and why you don't have a grasp of why void ratio matters. Because this view you see in Wikipedia is widely held in academia. And many faculties have made a deliberate and conscious choice not to teach the theory. Now, there's a problem here, because even though the people in Cambridge were the first ones to pull the math together, they didn't invent this. They were working or basing their work on contributions or building upon contributions by others. And what I put here on this slide, in the center block in the various colors, is a topic. And this is a topic which is underlying critical state soil mechanics, original CAM clay, the model you've just seen. Stuff coded in pink is a basic contribution to applied mechanics. Contributions made in orange are topics related to sand. Contributions related to clays are color-coded in brown. And as you can see, we can jump around from mechanics to sand to clay. The same framework or the same equations apply. It's just a question of detail, which is the most convenient soil to test. On the left-hand side is dates, when the contribution was made. And you can see we've got near 100-year history behind us here. On the right-hand side are the university where the contribution originated. Color-coded, the blue ones are British universities, the red ones are US universities. And you'll recognize from those university names, these are world-class universities, were and still are. So the question you have to ask yourself, when you look at this history, it's not good enough to say that CAM clay is over-idealized and misleading, because it works well some of the time. What you really need to do is pose the question, how can a 100-year history of mechanics, how can the math be that wrong? So rather than being rude about CAM clay, in the British vernacular, giving them a kicking, I see massive intellectual sloppiness by the universities. The question should have been asked, what has been missed? Now, to explain to you what has been missed, I need to take you to the Arctic. What you're looking at here is the north coast of Canada, and the yellow line is the border between the US and Canada, and it's Alaska to the left, as I've indicated, and the Yukon Territory to the right, which then moves across to the Northwest Territories. Just off this slide to the left is Prudhoe Bay. Prudhoe Bay is the one of the most productive oil fields ever discovered. It went on stream in over 40 years ago. At its peak, it was producing a third of the oil produced by the United States or used by the United States, and it's still producing today. The geological conditions on the Alaskan North Slope in the Devonian formations extend across into Canada. And the Canadians have been well aware that there should be enormous wealth in the Beaufort Shelf of Canada, as well as in the Alaskan side. And this idea was been around by Canadian oil exploration geologists for a while after the Prudhoe Bay was discovered. But what gave it legs, shall we say, it was the Canadian government in 1980 made a policy decision that they wanted the Beaufort Sea explored as a national priority. And so we went looking for oil in the Beaufort Sea. One of the companies involved was Gulf Canada Resources, and I was with a civil engineer with their frontier development group. And our acreage, or our leases, were pretty much where I've drawn Gulf Canada Resources on that diagram. We were in water depths of 20 meters, extending out to 40 meters. That is in the order of something like, depending on where you measure, something like 40 kilometers to 80 kilometers offshore. Now, we are well inside the Arctic Circle here. We were operating, or our staging post was that little crosshairs in the middle, that's tucked to the uptuck. We built a gravel airstrip, and we were on a 5-hour 737 flight from Edmonton to land on that gravel airstrip. We then hop onto helicopters to go offshore. So we're well up in the Arctic. And the catch of being in the Arctic is the sea is frozen 9 months of the year. And now this is not a very badly designed ship going from left to right. This is the Gulf exploration platform, the Moloch Pack. And she's sitting on the seabed, and that is ice flowing past her. This is quite early on in the winter. And the ice you're looking at there is about 0.5 meter thick. The Moloch Pack, and that's by no means as thick as the ice gets, the Moloch Pack is actually designed to resist 5 meters of ice pushing against the rig. How did we achieve that capability? Well, the answer is shown in the inset here. Even though that structure looks impressive, and I should mention here that she's about 100 meters across on the waterline, it's actually just a giant box. Technically, it's a caisson, and we fill the center of the platform with sand. And it is essentially a giant shear box. And that is how come a geotechnical engineer like me came to be engineer of record for deploying this platform, because even though the steel looks impressive, the steel is just along for the ride. It's a sand-filled structure. Now, at this point, I should also mention when the ice crushes, it causes a lot of vibration. And whereas you have a severe earthquake, the vibration might go on for perhaps 10 seconds or 20 seconds of severe shaking. With this platform, when the ice can move past it for hours. And I'm sitting here as engineer of record. I'm using hydraulically placed sand. I'm well aware of this history of hydraulic placed dams failing. I know all about the vulnerability to cyclic loading. And I am just one paranoid engineer. So what am I going to do? The answer is I follow Colonel Lyman's, or the Corps lead. I'm going to condition my decisions on whether it's safe to drop the platform onto the berm, whether it was safe to operate in winter, or whether we need to compact, based on the critical void ratio. Now, bear in mind this is an exploration platform. She's got a constant set down depth of roughly minus 19.5 meters. So as we go from site to site, and we're going to move her every year, we just deballast her, float her, tow her to the next site, and plop her down. We have to sit down at a constant depth. So we actually have to build a sand pad underneath her so we have a constant set down depth. We actually call those pads berms. And usually the seabed was soft clay, so we had to scoop out the soft clay because we were dumping some pretty hefty loads. I should say in terms of load, the horizontal load we were designed against was 50,000 tons, straight horizontal load. So we construct these sand-filled berms, and when we got the berms built, we ballast the platform down. I want to show you now how we are building these berms. That's key to our story. Now, nobody's ever seen a berm. They're underwater, so they'll never be seen by human eyes. So everything is done using remote sensing and echo sounders and such like. So we're building this using remote tools. And what you're looking at here is a photograph taken of the computer screen plotting up our survey data. A design drawing for the berm we're trying to build, and the blue and green lines are a couple of survey transects which we're checking out how well we're doing. And what I'm going to show you now is how the sand goes into place. So I'm going to show you how we put the sand into place to fill in that, bring the fill up to where I want it to be so I can put my platform down. So here is my dredge coming onto station. This is the Geopodis 9. I'm taking this photograph from the stern of the survey vessel, which we'll use to test the berm. And here is the same ship 5 minutes later, and I've put they have put 6,000 cubic meters of sand into my berm for me. And how are we controlling the process? Well, this inset photograph is taken on the bridge of the dredge, as I'm showing you there with the arrow, and the photograph is taken from the helmsman's station. That there is the Hewlett-Packard computer, which is been loaded with our design drawings. Off on the right-hand side is the orange box is a Solidus position fixing system. This is in the days before we have GPS. So what we have to do is, well, we had to build some shore stations so we could give ourselves a 3-point position fix wherever we were in our lease area. And that is what the orange box is doing. And the orange box is then interfaced to the computer. The ship's gyro is then also interfaced with the computer. So the computer knows from our design drawings what we want to do, and it knows where the dredge is and where the dredge is pointing. And what we then do is use the computer to generate a cartoon on that screen there I've just highlighted in blue for the helm of the dredge, or the captain of the dredge. And what we do is we show him a cartoon of his ship, or a little a yellow object with a pointy end and a blunt end, and we show some dots behind it where his ship has been, and we show in white lines the outline of the berm, and for any particular load we give him a green box, and the green box is where we want the dredge to be placed to discharge the sand. So in effect, the captain has just got a video game, follow the video game, which we provide to him, and we get ourselves a berm. Now, I've mentioned that I'm a paranoid bunny. And believe me, I'm really paranoid. You can't walk on this berm. You can't see this berm. And we're going to ballast a platform down on it. So the one thing I'm going to do is I'm going to test this berm very thoroughly. And the test we use is the cone penetration test. And that's what this guy in the orange suit is holding. He's holding our cone penetrometer. And for those of you who are not familiar with it, what we do is we measure a tip resistance, a friction ratio, and a pore pressure down at the base of this thing. I should mention here that I'm working for an oil company. When these penetrometers first came out, they were fairly crude devices, and they produced their output as a paper chart. You can't really manipulate a paper chart. You can't do much with it. I'm with an oil company. I've got money. So we actually had CPTs fabricated for our purposes. And the chap who did it, the chap holding the cone, is Lennart Jonsson. He's the electronics engineer who produced this equipment for us. And it was Geotech AB out of Sweden. And the reason we have an electronics engineer like this is we've got a downhole microprocessor. So we have temperature stabilized transducers, and we have downhole analog to digital conversion, and we have digital transmission. And we restore the data in digital form on a computer. And this is 1984, remember? At this point, the PCs have only just come out. But what we're using is top quality industrial instrumentation. This is a Hewlett-Packard computer, and we wrote the software ourselves. Or rather, we had a very talented software engineer from Gulf Systems Division who was given to us to produce the software. And then what we get on the right-hand side is what we want in engineering terms, dip resistance versus depth below the surface. Now, if you've been paying attention, you'll realize what I'm really interested in is the void ratio, more point the critical void ratio, and where I sit with respect to that. Well, the tip resistance is not a void ratio. I have to convert between the two. So how do we do that? Well, and this is an industry approach, we all do this, and all people using CPT correlations, this is what they're based on. What we do is we put sand in a tank. This, in the middle of the left-hand slide, is what amounts to a giant triaxial cell. This one is 1.2 meters in diameter. And what we do is we carefully place sand in that to a known density. And we have rubber membranes on the top and around the side, which we can pressurize. So I can stress this sand to a particular radial stress, and I can stress it at a particular vertical stress, and they don't have to be the same, so we can explore different stress combinations. And when we're happy, we then just push into that stressed sand our standard cone penetrometer, and we then measure tip resistance. And I can then generate from that, if I do a point on a tip resistance versus a confining stress, I can put a point on it for a particular void ratio. And if I do this a number of times, I can generate a map of tip resistance to void ratio to mean effective stress. And I can then use that map to convert my tip resistance data to void ratio form, which is what I've done here. This is the same data I showed you a couple of minutes ago, and it's now been converted using that map into void ratio versus vertical effective stress. This is an E-log P plot. My question for you people now is, where is the normal consolidation line? The reason I've spent that time showing you the dredge, they're very pretty photographs, but the real purpose of the story is I hope you agree that what I have shown you is the idea of the geological ideal of normal consolidation. Sand particles rain down under their own self-weight in water into position. And the soil has accreted by that method. That is the geological perfection for normal consolidation. So the question is, okay, we've done perfect normal consolidation. Where's the normal consolidation locus? Is it there? Or here? Or here? Or here even? In fact, what you see, you've got a complete zone of it. So let me now bring into the picture our yield surface, our cam clay yield surface. Now, bear in mind, my berms are more or less low aspect ratio structures. I'm actually testing here in the middle of the berm. So this really is 1D consolidation. When you do confined consolidation, your stress path on a QP plot is more or less where I've drawn that dotted blue line. Something, it depends on the material properties, but it'll be in that order. And the point of this is that where that blue line crosses the yield surface, that is your normal, that's where your normal consolidation locus is. So the corollary of what I'm observing here with my CPT is I've got a wide range of those normal consolidation locuses. That means that I've got a lot of yield surfaces here, and the yield surfaces are moving around because the line I've drawn in light blue, the two endpoints, they're one in the same place. So what we have here, we see from CPT testing that that green dot is not the critical state. So this was the problem with, or the issue with cam clay. They have made, it's not really an error, they made an unnecessary assumption. And this insight came out of careful cone penetration testing on a hydraulic fill. And this insight is the origin of Norsand. Now, at some point, you've got to do the math. It's fair, you know, you can say, okay, we understand why cam clay doesn't work, but that, frankly, if I'm going down that road, I'm showing the same intellectual inadequacy I criticize the universities for. So we need to do better. And the way we do better is this. When you look at this diagram, this is back to Casagrande's canonical diagram. This labeling ABC is Casagrande's labeling. And the implication is that somehow we have observed stress strain behavior in sketch A. We may put a constitutive model to that stress strain behavior. And an outcome of that model, or that understanding, is an evolution of void ratio, which is on plot B. And somehow we magically wind up with the critical void ratio, and that varies with confining stress, which is plot C. So the logic from Casagrande and the logic most people have pursued is we start with some sort of constitutive model, and everything else is kind of a consequence for it. And what we did here, or what was done, is that actually that is taking it the wrong way around. Back to Reynolds' cartoon, which is bottom left, what we took the view that it was actually particle movement that was the key here. And so we said, actually, this diagram should be read the other way around, that we have some reference state, which is in C, and we're going to evolve to that reference state with distortion. Now, all Casagrande has given us to work with is a schematic illustration. We can't work with a schematic illustration. We've got to do some math with it. And the math is cleanest as if you put together a deviation measure. So the pink dumbbell shape on plot B is our deviation measure. It's what we call the state parameter. And it's simply the current void ratio minus the critical void ratio. Once you've defined a deviation measure like that, then all Casagrande's idea is very simple. They say whatever the shape of the critical state locus, and however loose or dense we are, all his idea is that deviation measure, the state parameter, tends to zero with distortional strain. So I now have an evolution rule. And then we're going to formalize it around that. And we formalized it, said, okay, let's be absolutely explicit about this. I don't want to argue this on experimental data. I'm going to argue this mathematically. So we said, we're going to call this two axioms. Axiom one is an existence axiom. We just say that a unique critical state locus exists. And it doesn't have to be a semi-log shape, it just has to be unique. And axiom two is we're going to take this idea of our deviation measure tends to zero, but you do a bit of math around that, and it turns into a differential equation. We say is dpsi, the change of state parameter is minus that x thing is actually the Greek letter chi, times the state parameter times the distortional strain increment. And so that's where we came out. Norsand, we said, no, Norsand is not going to be a stress-strain model. Stress-strain is going to be a consequence. It's going to be an evolution of void ratio model. So what does this look like in reality when we turn it into yield surfaces? This is Norsand yield surface as a schematic. First off, you'll see the blue arrow, which is annotated flow rule. And we're going to keep the same Taylor-Bishop strength model that you have in original CAM clay. We're going to keep the normality condition of the theory of plasticity. So we have the same yield surface and more or less as CAM clay. So that dark blue bullet shape, I've got the same yield surface. The big difference is I'm not going to have my yield surface intersect the critical state. From what I've shown from the CPT data, we've got a range of yield surfaces. So they're all going to have different orange dots. And what this orange dot is the critical state has actually two conditions. And the conditions are shown on the top of the slide in orange. Condition number one for the critical state is the dilation has to be zero. But there's also, this has to be combined with a second condition, that rate of dilation has to not change with further distortional strain. The critical state is if you will, a dynamic, stable condition that can continue in perpetuity. At the image condition, we're only meeting d equals 0. So we said, okay, I've got my axiom 2. What's my axiom 2? My axiom 2 is very simple. That orange dot has to move to the green dot, and the green dot is my current critical state with distortional strain. Now, in fact, the green dot may also evolve, and the orange dot certainly evolves, and that is our hardening rule. And that comes straight from axiom 2. There is also a corollary. You find there's a limiting dilation that also comes out of the second axiom. So the pink arrow is a limit we put on the yield surface. We have an internal cap, and that stops it dilating too much. And that's it. That's Norsand in a cartoon. That's all there is to it. In terms of equations, the equations look like this. There are, as I say at the beginning, all plasticity models involve a flow rule, yield surface, and hardening, as I've indicated in each case what they are. And as you can see, they are 4 very simple equations. And that's it. The MI term in there is, you might think that's a material property M. No, it's a little bit more sophisticated than that. MI will evolve, and it depends on the grain shape, and it depends on the mineralogy and a few other things. So we make MI a function. Now, MI is an effective where we put an idealization in. And in the implementation of Norsand in Plaxis, we give you a couple of choices. more choices will come along as we learn more about soil behavior. I know, for example, if we apply Norsand to residual soil, we have to make M something that degrades with strain as the soil structure is destroyed. And that's it. And the only catch here, if it is a catch, is you have to solve these equations simultaneously. And certainly, I do not believe that will ever be a closed form solution, this set of equations, but they're trivial to do numerically. So let's see how the whole system works, or whole scheme works. This is the test I showed you earlier, that cam clay was out by order of magnitude. Well, what you're looking at here, top left is a stress strain plot, bottom left is the volumetric strain plot, top right is stress path, and bottom right is the evolution in E log P space. And you see we got an absolutely superb fit. And the important thing here is now, without changing the soil properties at all, I just changed the void ratio. And I can now do, for example, an extreme static liquefaction, which is what you see here. And at this point, people will say, okay, Mike, you're just showing us triaxial stuff, but all our stuff is 3D. Okay, well, here's pure silt in plain strain, Norsand versus the test data. And the people say, well, okay, what about cyclic mobility under earthquake loading? Well, there we go. We can do that as well. In essence, we have now got a complete framework explains how void ratio controls every aspect of soil behavior. And that is the offer of critical state theory. We link mechanical behavior to void ratio, and we do it through the laws of applied mechanics. This is not some geological construct or some correlation. Now, what I've shown you so far is a bunch of equations and ideas. And to use it, you really need you've got two classes of inputs. You have properties and you have state measures. On properties, I've hinted at those as we've gone through the presentation. This is things like lambda, the slope of the critical state locus, M, the critical state friction ratio, this parameter chi, the dilatancy parameter. There's a couple more we'll come to in a second. And then you need state measures. You need to know what the state parameter is. I haven't mentioned over consolidation ratio, but that's also a state measure. And we also have elastic modulus. And we use elastic modulus as a state measure because it depends so much on grain contact arrangement. It seems better to measure it in situ than to do something in the lab. And in essence, properties are what we test in the lab. State is what we get in situ, primarily using the CPT. Let me take you through those items now in turn. When we do this work in the field, cone penetration test equipment often these days comes in a truck as a self-contained unit. And if we're mobilizing a truck with this, we often don't want to bother taking out a drill rig to the site as well. And the cone testing people have come up with a version of a piston sample that works with CPT equipment. This is called a MOSTAP sampler. It's what you see here. It's something we can push into the ground, and when we got to the desired target horizon, we just lock the piston and push the sampler ahead of it and retrieve ourselves the sample that way. And the key thing here is soil properties don't depend on void ratio, they don't depend on structure, they don't depend on stress history. So we're quite happy with a disturbed sample because we're probably going to reconstitute it. And in fact, we will reconstitute it. And what you're looking at here is a minimum or minimal set of testing to define critical state properties. And I've highlighted in the top right, it has to be on a representative soil. What we're going to do is determine the properties, because bear in mind the offer of critical state soil mechanics is explaining how void ratio affects mechanical behavior. To calibrate such a framework, you have to test over a range of void ratios. And we're going to infer or determine our properties by comparing test 1 with test 2 with test 3. If we use a different soil in each of the different tests, we'll get a nonsense. So what you have to do is take your sample, and you then have to slice it and dice it into a number of representative samples, each of which is going to be identical, and you'll test those identical samples. And what we do here, test A, which is the top one, going horizontally, that's an undrained isotropic triaxial compression test from a loose initial state. And the test B is the similar loose one, but we now test that one drained, loose drain test. And the endpoint of those tests gives us the critical state locus, which is what my dotted green line, which isn't showing up too well. And that gives us the properties gamma, which is the altitude of that line, the property lambda, the slope of the line, and the friction ratio in the critical state. So I could pick up 3 of my material properties that way. The remaining properties, I'd have this test C, which is the dense one, and you actually have to numerically differentiate that into a stress to latency form. And we then compare the maximum dilation rate with the state parameter, which is the difference in the void ratio, the maximum dilation from the critical state line we just defined. That gives us the property X, or that's actually the Greek letter chi or chi, and then N, which is we can do that by comparing the peak strength and at that peak dilatancy. That gives us the volumetric coupling property N. That's it. Now, in reality, not all lab tests go as you'd hope, and people these days like to try and get to the more precise critical state locus. So a common test program will be 5 to 8 triaxial tests. If you're only doing simple bit of engineering, you might be happy just with 1 representative soil. If you look at these failure investigations of dams that failed, typically we will pick on a characteristic gradation, or an average gradation, and then we'll take a step out fine gradation and a step out coarse gradation. So we commonly will repeat this process for 3 characteristic or 3 representative soils. One property I haven't taught you about is stiffness. There's actually if you look at the equations on the hardening law, there's a property H involved. You can think of this property H as kind of an initial stiffness in a triaxial test. We don't like doing that because, in fact, H appears everywhere throughout the whole evolution of the soil behavior. So what we like to do is to take the test data and then guess H and compute a Norsand stress strain behavior using the guess value of H and see how well it fits the data. And then we keep adjusting H until we've overlaid as best as possible our theory on top of our test data. So we do a constrained optimization. It's like a video game. So here's the summary of properties and what they mean at the simplest level. And you know half of these properties yourself. And these are not rocket science properties. They're easy to understand. They are, the only one that's Norsand specific is H. Every one of those others is just the way soil behaves. And they're easy to understand. Okay, now on to determining soil state, the other side of the coin. Quick slurp of water there. The CPT is our reference test. This is no change to existing practice. The data evaluation method does change. We pick up elasticity from geophysical methods. We're going to use a seismic cone. This is already common practice. We will assume a Poisson's ratio there. We typically take it out as 0.2 or 0.15. That's based on a whole lot of testing done by the Italians on Ticino sand. There are other tests. The self-bore pressure meter is occasionally used. Some people like the dilatometer, but really the body of the experience is back to the CPT. So how do we get the state parameter from the CPT? Well, this is the chamber I showed you earlier, and it's exactly the same thing. But the difference is, rather than putting our map between tip resistance and void ratio, we make the map between tip resistance and state parameter. Just remember the state parameter, this cartoon on the bottom left, the green line is the critical state locus, and the purple dot is at the current void ratio, and the state parameter is just the difference between those 2 void ratios at that particular confining stress. So it's very easy to take the test data, which is given in terms of void ratio, and convert it to a state parameter. And this is an example of what you find when you do that. The little dots on the graph are individual results of a chamber test. And what you find is you get radial lines with state parameter, as I've indicated there. And slope of a radial line like that is this parameter Q, which is a normalized penetration resistance, or QT over P. Those of you who have a background in deep foundations, this is exactly the same parameter we would use in a pile design, except in piling engineering, we would call it N sub Q rather than Q. But the in-situ testing folks, we just use this parameter Q rather than N sub Q. And what we do, we plot the data up as Q versus state parameter. You get this, a trend line like this. And I emphasize here, this is not a correlation. This black line is a theoretical expectation. All we're using the data to do is to calibrate our theoretical expectations. So M and K in here, what we call inversion coefficients for the CPT. Q is what we measure, or a normalized version of what we measure. And psi is the state parameter we want to determine. Now, there's a small wrinkle here. What you're looking at here is the results of this calibration testing on, I think there's 12 sands on the screen, it may be 10. And we always get this semi-log line, or very close to it, the theoretical expectation. But different sands give you different lines. And this is a problem, because if you look at a typical hydraulic fill, I'm showing there on the red line the sort of number we would find in many of our hydraulic fills, or our tailings. And the problem is simply this. If I've say, I'm looking at, I think it's a Q value of 60 if I can read the screen. If I'm on the bottom calibration, which is, I think it's Reed Bedford sand, I would say, okay, I've got a state parameter of minus 0.14. At that point, I'm a very happy bunny. Nothing bad whatsoever is going to happen to my structure, my soil. It's going to be very dense and very dilated. Conversely, if I'm having to use the calibration for, or it's appropriate to use the calibration for Toyota sand, which is the light blue line, my state parameter is something like minus 0.02. I'm getting very close to static liquefaction territory. And notice here that my decision as an engineer of record depends every bit as much on which calibration is appropriate as what I've actually measured with the CPT. So I must pay attention to my calibration. Now, in the in-situ testing literature, this issue of a range of results and calibrations chamber by soil type has been known for perhaps 4. And people say, if you look at the various papers, this is down to compressibility. The different compressibility affects different tip resistances. Now, I say, well, that's all very nice, but what is this compressibility which you speak? How is it measured? How is it defined? And have you indeed shown it is only compressibility that matters? At this point, you've really got to roll up your sleeve and do the math. And the math we did was the standard thing. We looked at cavity expansion theory. And we do that because it's the cone testing. It's you know, when we talk about soil mechanics, we're much more used to talking about stress and strain as where our reference point. But when you think of a cone going into the ground, this is much more like a hydraulics problem where soil is flowing past it. So we really should be talking in terms of velocities. And that is an aspect of soil mechanics we just haven't got to doing. So what we do is we say, okay, well, the pressure on the tip of a CPT, and you look at my cartoon on the right, you'll see it's labeled pile, because this comes out of pile design. In fact, pile design comes out of punch indentation theory for metals. We take the pressure on the tip of the CPT as being related to the pressure required to inflate a cavity. What you see on the left cartoon is a green dot, and if we magically introduce pressure inside that green dot, we can inflate it. And if you look at the pressure required to inflate it, you'll find that you come to a certain point or a certain cavity when the cavity will now continue to inflate indefinitely at constant pressure. We call that the limit pressure. And what's happening there is, yes, it takes a bigger force to expand the cavity as it gets bigger, but the cavity area is also increasing, and the two just come into balance. That's why you get that. And this was actually the original motivation for Norsand. We needed to, remember, I'm going back to Colonel Lyman, I want to know where my critical state is compared to where my, and I've got to pull that off my CPT, I need to know which correlation I can rely on, or what I should be using. And that was the motivation for Norsand. We needed to understand the CPT. We wrote our own finite element code to do this, and it's fondly known as the CPT widget. And that is a component of what you will need to use, because you're going to have to go through the same process in using Norsand. Is you're going to have to work out what is the appropriate response for your CPT. And what we discovered is it's not just compressibility that matters. In fact, all the soil properties affect your calibration of your CPT. At this point, you say, well, okay, this is fine. How well does this work? Well, a chap called Mason Gafghazi, who's now a professor at the University of Toronto, he looked at this for his PhD thesis. And what he did, he took the database of calibration chambers, and he said, what we can do is these calibration chambers, they've report a void ratio, and each of these dots on the graph is a calibration chamber run. So you're looking at 331 calibration chamber tests in here. And they report a void ratio, and these people shared their sands with us. So we've tested this critical state loci, so we can convert their void ratio to effectively a measured or their reported state parameter. And they report, for each of those runs, they report a QC value. And we can take that QC value, we can take the Norsand calibration for their material, and we can run it through the widget. And we can then say, okay, based on their QC value and everything on their properties of that sand, we can compute a value of the state parameter. So what we're testing here with this figure is the reliability of the method in the round. Complete, this is the most. We're not just demonstrating we can compute a tip resistance, we're demonstrating the reliability of the process. What you see is the line of equivalence is perfect. And the 80%, if you look at the raw data, 80% of the results lie within plus or minus 0.04 of the line of equivalence. If you look at or you then dig into it and say, well, is this as good as we've got? The answer is actually this diagram grossly overstates the variance. Bear in mind, these chamber tests involve placing 2 tons of sand carefully, and more to the point, accurately measuring the void ratio of that. Well, that's actually, despite the CPT industry treating that as a gold standard, reality is a lot of experimental scatter. And virtually all the scatter you see on the plot here is actually down to the precision which we can do calibration chamber testing. Now, so far I'm talking about sands. What about undrained behavior? The answer is it's exactly the same, except instead of using Q, we use this formula of Q times 1 minus BQ plus 1. That is, we've got to introduce the measured pore pressure by the CPT into the framework, and the framework then continues. Okay. Now to the engineering use of this. The next thing we've got to deal with is soil variability. This is the CPT results which are associated with that tar island liquefaction failure I showed you. They are not from the exact slide I showed you, because they didn't have the CPT at the time. But the folks in the mind have continued placing the sand the same way, and it's the same sand, so we've just tested it later to see what sort of results would be representative. And this is what you see here. And you'll notice there's a lot of squiggles on the diagram. You're looking here at 4 CPTs. They're separated by 136 meters, 78 meters, and 82 meters, as indicated at the top of the slide. The top of the diagram in black is the top of the compacted cell. The orange line is the transition between compacted cell and tailings. So most of that black squiggle is the tailings. And the question is, how do I deal with that variability? Well, back to the Molik pack. What we did on the Molik pack, we actually took an interest in this issue of soil variability. And we started playing with spacing of the CPT to try and chase down how continuous were loose pockets and how continuous were dense pockets. And if you'll see on the top of the diagram, we actually brought the spacing down to 9 meters before we could reliably start seeing how loose zones and dense zones merged into each other. And You can see they're highlighted in dark gray is a dense zone, and down the bottom right, there's a loose zone. And what was then done, we then went to stochastic finite element analysis. What you're looking at in the top of this slide is what amounts to is a block of the Molecular pack. It's a Molecular pack core, and they've modeled that with 480 finite elements. And the plots, what we're going to do then is run an earthquake past those finite elements, and we're going to use one of these constitutive models that computes pore pressure, and it's sensitive to void ratio. So we can look at the effect of void ratio on the excess pore pressure. And you can see the scale for excess pore pressure on top right. In essence, dark black is full liquefaction. Pale gray is an RU of 0.6 to 0.7. The results I've circled in blue and I've called stochastic. Those are 6 individual, what we call realizations of the model. Each of those, what we've done is we've populated our 480 elements randomly with void ratio. The random choice of void ratio honors the standard deviation and the trend of mean that we see in the CPT. So we're replicating the statistics of our sand. Now, of course, it's a statistical business. So that's why we roll the random number generator, and each time we roll it, we'll get a slightly different distribution. What they've then done is they've computed for the extent of liquefaction under their standard earthquake. And you can see 6 different pictures in the top in blue. In pink below, we've then done the standard calculation where the sand is now all at 1 void ratio. And the top left one is where we use an average void ratio corresponding to, or with trend with depth removed. The next one across is where we use a 50 percentile or a median void ratio. The top right one is where 60% of the void ratios are denser than what we've used in the simulation. And the bottom left is 70% denser, 80% denser, and then 90% denser. So we're looking at the distribution and saying we took one value from that distribution, what would be representative? And judgment involved here. Quite clearly, if you're operating saying the loosest 10% controls, which would be the bottom right cartoon of the pink plots, that's a little too conservative. Nothing in, most of the time, well, nothing at the top is as bad as that. If you look at the 70 percentile, which is the bottom left in the pink area, to be honest, everything in the blue zone is pretty well worse than that. So my own personal pick is I like running with the 80 percentile. So what do I do now? This is the same data. This is back to our entire island thing. I've taken my wiggly CPTs, which is what I showed you earlier, and I've converted them into state parameters using the widget. And this is how they plot up. And I then got to make choices of what is characteristic. And you can see in the black vertical lines, this is my characteristic choice. And this is the values we used to produce the simulation I started this presentation with. With this set of choices, we actually calculate 4 meters of settlement versus 5 meters measured. I think if I look at this now with hindsight, I should have taken a slightly more contractive pick of the state parameter at the bottom. But this is something you have to do yourselves when you look at your own case histories. We're giving you a very mechanics-based approach, but at the end of the day, there's still a good chunk of engineering judgment as what is appropriate. I'm sketching out for you now the basis on which you make these judgments. Okay, quickly now. When you do, we want to pick up the Gmax. Okay, that's easy. Every cone testing contractor on the planet now puts a seismic module on their CPT, so it's virtually free data. We just measure it as we go. If you're in the lab, what we ask you to do is to use Bender elements, which is what you see in the bottom left of the photograph. So a little micro or very small piezoelectric transducer we put in there to triaxial cell, and we can ping a seismic signal as we're loading the soil to in a traxel cell. So we can pick up Gmax that way. Okay, we're just about at the end now. And using critical state soil mechanics, the important bit. What I've sketched out for you in this last hour, I've taken you through the theory, its origins and its equations. I've done it quickly, but you know, you can see the framework. I've told you about the properties, what they are and how they're measured, and hopefully you can see that, yeah, you can get your head around those. And the state parameters, it's all anchored to the CPT. Perhaps there's some different data processing to learn, but you know, this is not rocket science here. But what about you? You folks are the important bit in this. You need to be confident in your approach, and we need to fix what's been missed in your education. I've given this talk a number of times, and people follow along on every slide. And at the end of it, they said they would come up to me and say, "Well, my brain hurts. What on earth? How on earth does this all work together?" And all I can do with you in a presentation like this, I can flag up to you or advertise to you what the framework is. But you can't. You're not going to learn it in an hour in a webinar like this. You've got to do something for yourself. My suggestion to you is to get yourselves comfortable. The first thing you should do is pick up PLAXIS. PLAXIS has something called a soil test mode, which it will compute for you a lab test. And I show on the screen here, this is the PLAXIS soil test mode, and it's set up for a traxel test, and this is a loose liquefying traxel test, so you can see the stress path on the right and the stress strain behavior on the left. And you can't break the model, just change the state parameter, just look at drained versus undrained, change the property lambda, change the property m. You can use this as a learning tool to get a feel for how Norsand works. Having got a feel for it, you can also bring in your own test data and have a look at how well does it calibrate to your test data. And there's a serious point here, because as an engineer of record, you should not be producing a judgment saying, aha, I have this reference and Mike says this, and because Mike said that, here's the reference to Mike saying this, ergo, this is what I'm using. No, 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 no. You must follow the Russian proverb as an engineer of record. Trust is wonderful, distrust is better. What you must do is say, okay, how well does this framework work for the soil I'm engineering? For yourself, that yes, this actually fits your test data. Check it fits your stress strain curves. Now, what you really, or how are you going to start even beginning to think, what do these properties mean? Well, as I say, every time I give this talk, it produces a universal reaction, well, usually anyway. Great talk, Mike, but how on earth does it all work? This talk started out as a talk for the Cross Canada lecture tour in 2012. And the most interesting reaction was in Vancouver, where they said, great talk, Mike, but please come and explain to us how it actually works. So we created a course for the Vancouver Geotechnical Society. And that course has now been given worldwide, I think about a dozen times. But we redid it in Vancouver in 2010. And if you go to the Vancouver, when you leave this webinar, you can go to the Vancouver Geotechnical Society website. You can find them easy enough on Google. And if you go to them, you'll see they've got a topic called Other Events. And you pop onto there, and you'll come up with 2010 Critical State Soil Mechanics course, or short course, CSM course, short course, I think it is. On that link is a very good manual. There's I think it's about a 50-page booklet on which gives you in 50 pages what I've more or less taken you through in this last hour, which you can read at your leisure. And not only that, we have put all the slides, all the slide decks for the course on there as well. So you can download and leaf through the slides, and you can basically bring yourself up to speed. And that's where I suggest you start. Hopefully I've enthused you in what's on offer here with critical state theory. And if I've succeeded in that, this is probably your first port of call. And I think, oh yes, I'm not quite finished. Don't forget the foundation. This talk has very much been conditioned around liquefaction. Those of you in the liquefaction business will recognize these case history names. These are all famous, quote unquote, liquefaction failures. In reality, in every one of these, liquefaction was secondary. All of these were foundation failures. I'll point out here that Norsand will do a great job of a brittle foundation. You know, it's a universal model, but please don't forget the foundation, because the foundation is what's causing at least half our troubles. You know, bromide is actually quite rare in being a true simple liquefaction. Aberfan was another one, but most of these events are foundation movements causing distress in the tailings, and when one builds on the other. And that's why you need the finite element analysis, because it's not a simple, oh, it's just a SU in the tailings. No, no, no. It's the SUs being affected by the way the tailings are moving. The tailings move because it depends on how the foundation is moving. So you do need to really think about foundations. Just keep at the back of your mind. Half these failures are foundation failures. Andrew, over to you.
Thank you. We have a few questions, Mike. I have selected some for you. Probably we will not be able to reply to all of them because they are a huge list, but I can just push some. This is first one.
Where does the Norsand name come from? Yes. This is a question I get asked a number of times. It's a nice story. The starting point is